what was the context in physics before special relativity that led or formed the furnace out of which, or maybe the crucible is the right word, out of which special and general relativity arose?
Couple historical things to understand, because the question you ask sounds perfectly reasonable and is perfectly reasonable as a question.
Thanks.
But the answer isn't the kind you're looking for. And this is part of why there's a lot of misunderstanding about both those theories, really. The crucible from which special relativity came was the inside of Einstein's brain.
Okay.
It wasn't, I mean, remember how young he was, right? He was in his, he was a patent office clerk, 1905. He was not steeped in the whole, milieu of theoretical physics for a long time. And when you look at 1905, the so-called Annus Mirabilis, right? He's writing the paper that essentially proved that there are atoms, which was on Brownian motion. He writes the paper that basically kicks off quantum theory as we now understand it. I mean, there was Planck stuff before, but he has a paper on the photoelectric effect that is really the beginning of quantum mechanics. He writes on the electrodynamics of moving bodies, which is what we would call the special relativity paper. He writes another paper following that, E equals mc squared, okay? And this guy's in his 20s. What have you done recently? Okay, so what do we know? We know he had this amazingly fertile mind for physics. And the fertility came from a certain desire for conceptual clarity and thinking about, I mean, you can call them thought experiments, but it's a little misleading to call them thought experiments. Thinking about the implications of physics in very simplified situations, right, where a lot of the detail washes away. I mean, Einstein always talks about in his autobiography, even when he was a teen and he first learned about electromagnetic theory, Maxwellian electromagnetic theory, and the idea that light is electromagnetic waves. And then he asked himself the question, which, if you understand that theory the way Maxwell did, seems like a kind of reasonable question. What if I were traveling along with an electromagnetic wave? What would it look like, as it were? Or, I mean, how it looks is, of course, kind of metaphorical. But in the same way that you would ask about a water wave, I mean, imagine a wave in the ocean. You think, well, waves in the ocean, here's something that never happens, that can't happen, that there's a lump in the ocean and it just sits there, right? I mean, a wave travels.
Yeah.
And you can't, if you try to pile up the water to make a wave and let it go, it'll just, it won't do it, it'll just disappear. On the other hand, if you imagine a water wave moving this way, and you happen to be above it moving at the same speed, and you look down, you would see a lump of water just sitting there, right?
Mm-hmm.
You'd be a little surprised about that. And you'd say, what's going on? And you could finally work out, oh, I see, I'm kind of moving along with it. Now, Einstein said he exactly asked himself this question about electromagnetic waves. What if there's an electromagnetic wave and I'm traveling at its speed, or describing it, if you will, from the point of view of a frame of reference that's moving at its speed? Then it wouldn't be moving in that frame of reference. But then you're supposed to have this electric field and this magnetic field at right angles. They're in a certain state, and they're not doing anything. And he said, but there's no way to describe that using Maxwell's theory. He said something like, we never see anything like this, these sort of static electromagnetic bumps, if you will. That's something that bothered him as a teen. There's a historical error here that everybody repeats, and I'll tell you the little story about, we think, why people say this. So it became a standard thing to say, oh, the great ferment over electromagnetic theory was the Michelson-Morley experiment. because they'd been looking for evidence of this electromagnetic ether. I mean, just again, to walk back a second, you have Maxwellian electromagnetic theory that postulates these new objects, new physical ontology that they called fields. There's nothing like that in Newton. Electric field, magnetic field. Maxwell writes down some equations. And again, you have to remember a little bit, if you've learned this stuff in school, when we present Maxwellian electrodynamics, it's usually with like 4 equations. What Maxwell wrote down was 20 equations. And so Maxwell has these ideas, and there's kind of a lot of mixture of all sorts of different physical problems, and he kind of has this whole pile of ideas. Later, Heaviside reduces all of this to this kind of much cleaner presentation where there are only 4 equations, which is normally the way we learn it now. Einstein had the benefit of that simplification. So in a way, he learned a simplified version, if you will, or cleaned up version of Maxwellian electrodynamics, which meant that, again, with his kind of mind, he could think, what would happen in this situation? What would happen in that situation? Anyway, people were puzzled at the end of the 19th century about these fields. What were they? Because they weren't like anything Newton had. And they're defined everywhere. Unlike particles, which are always somewhere, fields are always everywhere. And there was this, it wasn't an empirical problem. It wasn't that Maxwell's equations were making bad predictions, but people were just puzzled. What are we even talking about?